10, and we're going to work through this. As you guys know, we have our slope field quiz today. Maybe that's why you guys are doing slope fields. You're like, I'm ready for slope fields. That's not a bad sign. That's not a bad sign. So if we get, hey, will you guys help me out with this? If we get to 20 till, big hand on the 8, if we get to 20 till, and I haven't started to transition over to a quiz, remind me, hey, we got a quiz to do. Okay, so I'm sorry about this. In your packet, I think has a typo. Yeah, it does. So if you would, look at number 1. I'll just give you a minute to look at this. A and B have typos on yours. So your option A should be dBdt equals KB, and option B should be dBdt equals B over K. C is fine, D is fine, as they are both written. So what I want you to do here is basically a translation. So not really a whole lot of calculus. This sort of, maybe a little bit, but not a ton. Mostly just translation. It says the rate of change of number of bunny rabbits in a field is directly proportional to the number of bunnies in the field. Which equation describes this relationship? So circle one of those 4 options you can discuss. And this will kind of be our jumping off point for what we're going to do today. We just have 2 examples we're going to work through together. And hopefully some familiar examples, to be honest with you. These are very science, biology-oriented examples. Hope you'll enjoy those. So again, apologize for the typos there. A should be dBdt equals KB. B should be dBdt equals B over K. C and D are fine as written. Anybody have a inkling about this? Let's just start off with a showing of hands. How many of you think A is the correct answer? Raise your hand real high right now. Okay, handful of you, like maybe 4 or 5 of you. How about B? Raise your hand. How many of you think B is the correct answer? Similar number, about 4-ish, 5-ish of you. Okay. How about C? How many of you think C is the correct answer? Nobody's saying anything. Okay, how about D?
Wow, we got like 4 votes there.
Okay. No, there's total about 10. There's about 5 and 5, 5 and 6, something like that. Okay, so anybody want to explain why you because nobody seems to think that it's C or D. Why would you eliminate, and you are correct to eliminate that? What tells you up there that it's not C or D, Reese?
Well, because when you were showing the rate of change, they're both just...
Yes, so that's a great point. So it says rate of change is what we're supposed to be looking for, yet both of these are not rates of change. They're just number of bunnies. So really, when you see rate of change, doesn't the correct answer have to be dBdt equals something? It can't just be B, because B is not as defined here. It's not a rate of change. Okay, so then the key to differentiating between A and B is probably this word right here. The rate of change is directly proportional to the number of bunnies in the field. Directly proportional is actually expressed by this. Directly proportional means as one quantity goes up, the other quantity goes up. Okay? So would it be fair to say that the amount that you're willing to spend on a Chipotle burrito is directly proportional to the amount of enjoyment you get out of it? So if it's a really good burrito, the amount you might be willing to spend on it would go up. Right? If it's not a very good burrito, the amount you'd be willing to spend on it would go down. So a directly proportional relationship means when one thing goes up, the other one goes up too. Inversely proportional means when one factor goes up, the other one goes down, or one goes down, the other one goes up. Anyhow, so does that make sense? dBdt equals KB as far as a directly proportional situation. So what we're describing here is something that you've probably referred to in the past, and you hear people say all the time. This is actually referring to something called exponential growth or exponential decay. Okay? And some people joke that bunnies multiply exponentially. Does anybody know the gestation period of a bunny? Like the time from conception to birth. You know how long it is?
1 summer. 2 months.
Slightly less than a month. It's like 28, 29, 30 days, something like that. It's basically a month. So that's why when you see a field of a couple of bunnies, you know, a few months later, it seems like there's 10 of them, and a few months later, it seems like there's 1,000 of them, right? They do seem to multiply quickly. They have a very short gestational period. They don't truly multiply exponentially. There's other factors at play there, but they do multiply very quickly. So we're going to be looking, like I said, at some science-oriented examples here today. So let's do this one together. This is about bacteria. So this is a pretty good example, and the growth is eventually limited, but early on, it's a pretty good example of exponential growth. So bacteria grow in a certain culture at a rate proportional to the amount present. So I want to highlight that phrase for you. Bacteria grows at a rate proportional to the amount present. So based on what you did in number 1, could any of you interpret that orange highlighted phrase into a differential equation? So what you did in 1, it's just not multiple choice this time. Any ideas? Bacteria grow at a rate proportional to the amount present. Look back at number 1 if you need to. Any contributions? You guys just feeling totally in the dark about this? Luke, what do you got?
Well, the first activity would be dg dt.
Why G?
Just growth bacteria, or B. We could use bacteria. Yeah.
I think I'd probably go with B because it's bacteria. G for grow is more of a describing of what it's doing. It'd be nice if we said, because it's not the rate of change of growth, it's the rate of change of bacteria. But I agree, the left side needs to be a derivative, so let's start off with that. So let's go dB dt, and if we can agree on B as our letter, although, I mean, let's be honest, if Luke used a G, it's probably not going to make much of a difference as long as he knows what the G stands for. So I kind of like B here, but whatever. So then if it's dB dt, what does that equal? Say again?
KB.
KB, yeah, okay, so let's agree that that's what we're going to do. We're going to use the letter B here. So that is expressing the rate of change of bacteria being proportional to the amount that's there. So basically, the more of the bacteria that's there, the faster it grows. That makes sense? The more the bacteria that's there, the faster it grows. It also describes things like pandemics, speaking of like the coronavirus, that kind of thing. Early on, this very easily could describe it. Okay, so it says, suppose there were 100 bacteria initially and the amount doubles in 1 hour. How many bacteria will there be in an additional 1 hour? Or excuse me, 0.5 hours, 1/2 hour. So what we need to do here is we need to find the solution curve for B. So this will be a nice review of what we did yesterday, but one reminder for you, K is a constant, right? And so we're going to treat it like that. We're going to treat it like it's a 3 or a 2/3 or something, right? So the K is just some number. So my first step, bless you, as you remember from your warm-up, your first step is to separate your variables. Right now my two variables are B and T, right? So I want to get all the B's on one side, and I want to get all the T's on the other side, and I'm going to leave that K as a constant, right? So I'm not going to worry about moving that around at this point. Think about it for a second. Think about what that would look like if I got all the B's on one side. I've got to do this mathematically. Got all the B's on one side, and the T, all the T's on the other side. Bless you. Any thoughts on this? Where could the B go to start off with? Please don't do this quiet game if you have it. We don't have that much time. Yeah, Luke.
Well, you could just separate it out, and then the B could go like even a -1 dB.
Can I write it as a fraction?
Yeah.
So you're dividing both sides by b.
Yeah.
Yeah. Okay, so we'll do this in steps. So Luke proposes we write db over b to the negative 1, or not b to the negative 1, sorry, over b dt equals k, right? So basically what Luke has done there is he's divided both sides by b. And I think that's a good move, because do you see how he's moved the b over there with the db? But if we stop there, the dt is still with the b's. We're not okay with that. So what would I need to do to get the dt to the other side? Multiply both sides by dt. So wouldn't that leave us with this? db over b equals k dt. So remember, the k is a constant, just like a 7 or a 12 or something like that. So I've got all the b's on the left side. I've got the one t that I have on the right side. So I'd say at this point, all the variables have been separated. Remember, this is a really important step to show. All right, so then once I've separated the variables, remember that silly phrase, separate, then integrate, right? So we find our antiderivatives. So I'm going to do the antiderivative of both sides. The left side, what is the antiderivative of db over b?
Natural log of absolute value.
Yes, and this is where the absolute value will start to play a really important role potentially. So the derivative of the bottom, basically this is the antiderivative of 1 over b, right? 1 over b db. So ln of absolute value of b. And then remember the k is a constant, like 7 or 3 or negative 2 or whatever. So what do you think the antiderivative of k dt is? kt, very good. And remember, we customarily will put the plus c on the right side. Remember, that's just a combination of the two c's that would have showed up. And this is where these particular questions are a little bit weird, because there's two different constants that are unknown, right? There's a k and there's a c, and they're two different constants. Okay, they're two totally different constants. Okay, so this is where your calculators are going to come into play here. So let's find our c value first. Does anybody see an initial condition that might help us with our c value? There's two different initial conditions here. What do you see?
100 bacteria that are initially,
And what does the word initially mean?
that's what it was.
T is 0, right at the beginning. T is 0. There are 100. So what I'm thinking, we know that there are 100 bacteria. So this would be ln of 100. And I know that the absolute value of 100 is 100 equals k times 0 plus c. And I will come up here. I have a little bit more room. So k times 0 is just 0. So I get natural log of 100 is equal to c. Well, that's good news. So let's see here. I've got ln of absolute value of b equals kt plus natural log of 100. What do y'all think? So if you wanted to, you could approximate that natural log of 100 with a decimal. Just be careful that you don't round too early. Rounding too early will always make you be off by quite a bit. Okay, remember we're hunting for this solution curve, and I just figured out the c, but I also need to find the k, right? There's two different constants here. Does anybody see a different initial condition that might help me with my k? Yeah, what do you think?
There's 200 bacteria after 1 hour.
Yeah, it says the amount of bacteria doubles in 1 hour. Okay, so I'm thinking that would be ln of 200 equals k times 1 plus natural log of 100. All I'm doing here is I'm plugging in things, items, that actually make sense, right? So Hunter's saying, hey, doubles in an hour? Well, there were 100, and doubles means now there's 200. Okay, so finding the k, this would be natural log of 200 minus natural log of 100 equals k. This would be where if you know your log properties, this would make this really simple looking. Does anybody know what ln of 200 minus ln of 100 is?
ln of 2.
It's ln of 2, isn't it? Right? Natural log of 200 over 100. So we could just say natural log of 2 is equal to the k value. Gosh, that would make this one so much simpler. Those log properties do help. Okay. So here we go. I'm going to write this out with my k and my c. So this would be natural log of absolute value of b equals ln of 2 times t plus ln of 100. So I'm finally ready now to try to get this b by itself. Right? I've got the k, I've got the c. It's all evaluated there. This is where, honestly, this is where people will sometimes struggle because this is all algebra from here on out. Does anybody know a good first step on trying to get the b completely isolated? What do you think, Hunter?
Plug in T.
Plug in. What do you mean by plug in t?
We're supposed to find out how many bacteria there would be in intestinal.
Oh, for sure, for sure. So you're just aimed straight at getting to this answer. I want to get to the particular solution, and then I'll plug in the 0.5.
Okay.
Is that okay? Like, I don't think that you're wrong here. I want to get to I want to take a little bit of a side trail to get there.
Okay.
I do. I want to get the b by itself. So how do I get the b completely isolated and alone? E. You say E? Yes. So it's E both sides. So it's E to this whole left side and E to the entire right side. And the reason why I want to do what I'm doing here is I want to make a connection to like a pre-calc class that you've had in the past. You've seen these before. So if I do E both sides, what does the left side look like? Absolute value of B. Not just B, but absolute value of B. And then the right side, I'll just write it as E to the ln of 2 times t plus natural log of 100. Make sure that those two pieces remain in the exponent. Okay, so here is where the absolute values come into play. And this is where this being a practical example makes a big difference. Doesn't B stand for the amount of bacteria? So what couldn't the B be?
Negative.
Could never be negative, right? So we know that B is always positive. What's the absolute value of a positive?
Positive.
It's just itself, right? It's like the absolute value of 10 is just 10. And so the absolute value of B in this case would be B. We're actually gonna see some examples in the coming days where the absolute value of B is not actually B, it's something different. So we'll get there later. But for today, that's how it is. And then my last step before we would do the plug-in thing is this. Do you remember, can you see how on the right side we're adding exponents? Right, it's natural log of 2 times t plus ln of 100. We're adding exponents. Do you remember when you're adding exponents, what are you really doing? Say again?
Multiply.
You're really multiplying. That's right. So this is really b equals e to the ln of 2 times t times e to the natural log of 100. That's really what this is. So then, what's e to the natural log of 100? Isn't that just 100? So check this out. This is where I wanted to go. And obviously, at this point, we can just plug in very easily to answer this question. Have you ever seen exponential growth presented this way? Where it's b equals ce to the kt? Remember this from pre-calc? Where that c right here is the initial amount. Like, remember PE to the RT? Like I equals PE to the RT? Like for financial stuff, where that is the principal. That number is always the initial amount. Notice how we got there using calculus, right? And the truth of the matter is, when your pre-calc teacher taught you this, they weren't teaching you exactly where this came from. That's what I'm trying to do. I'm trying to teach you, where does this exponential growth or decay actually come from? This is it. It comes from a differential equation solved. So to go to Hunter's point, and I know I'm right up against my time that I set, to figure out how many bacteria there will be in an additional 0.5 hour, I would say B equals 100 e to the natural log of 2 times what number?
1.5.
1.5, right? Because if 100 is my initial amount, well, in an hour, there's 200. I want to know how another half hour. So it'd be, and if you wanted to, you could write it as 1.5 times natural log of 2. That actually might make a little more sense. Has anybody figured that out? what that B would,
82.843 bacteria.
282?
Mm-hmm.
282.843?
Yep.
So hopefully accurate to 3 decimals. If you did some intermediate rounding, that number will for sure be off. But so you don't want to be careful to not do that. That'd be finally getting to your answer right there. Okay. I think I'm good. You guys grab some fort making materials. I'm gonna set out some rulers as well. You can leave those whiteboards out. We're gonna use those in the next class. If you would make a fort, I'll hand out some rulers if you want them. Cole, would you like a ruler? I would. Okay. Nate, ruler? There we go. Jack, you keep the rulers today? Please make sure you get these rulers back to me. Maybe reuse them. Okay. All 3 of you guys want a ruler? Yeah. That'd be helpful. There you go. Rulers. Rulers for you guys? Okay, once you have your fort up and ready to go, we'll get you your quiz. Okay. So you can see there's front and back, basically 2 slope fields